Hello. In this video, I'm going to be talking about the bottom-up merge sort approach, specifically using a linked list. And this is a very important concept, especially when you are maybe looking at leak code or interview problems, or maybe for an assignment. I wanted to create this video because I didn't think there was a lot of information or a video that kind of broke everything down. And so once I kind of figured this out, I wanted to kind of share the information and pass it along just so it would be clear to other people. This video is going to be split up into different sections. This video is going to be a little bit long. I'm going to start with just talking about merge sort in a broader sense, very briefly, and then I'll go into these different sections of the bottom-up approach. So I'll include the timestamps so you can skip around and find the place or location if you needed a specific more clarity or more information on a specific section, just so it's a little bit more organized and clear. The first part of this video will talk about the introduction to merge sort at a higher level. Looking at merge sort, we first want to consider these three different aspects of merge sort: understanding divide and conquer, understanding merge sort as a sorting algorithm, and also understanding how it comes to an n log n time complexity. The divide and conquer from merge sort comes because we are splitting up that list into halves, and then we're performing this merge and sort in a recursive manner. So when we think about this pattern of recursion and splitting up those halves and merging and sorting them together, we're trying to solve that problem of sorting using this divide and conquer by separating it into those halves. Looking at merge sort as a sorting algorithm itself, we have to understand that because we're using recursion and we're going through the stack and memory space, it's not considered an in-place sorting algorithm. And even though we are not explicitly creating another array or adding or creating a copy of the array to allocate or solve this sorting algorithm, it's still considered additional space if you use recursion in this way to kind of sort or solve the problem. And we also can consider that merge sort is stabled. So if there was two equal elements, if there were two 4s or two 5s at different locations within the list and we use merge sort, those numbers would still keep their location. The first 4 would still be before the second 4 and wouldn't be modified. So looking at the time complexity, we can consider that since we are splitting the list in half every time, this is thinking about reducing the time by a power of 2. So it's not dividing by 2 every time, but the first time we're splitting it by 1/2, then the second time the list is split into 1/4, and then 1/8. So it goes through that pattern, and thus it would be considered a log n time. And since it takes a linear time to merge and sort those lists together, then it would be the n log n time complexity. The top-down versus the bottom-up approach to merge sort is looking at the difference between performing merge sort recursively versus performing merge sort iteratively. Looking a little bit closer at the top-down approach to merge sort, this is probably the merge sort that a lot of people are already familiar with. We start with this list, and we will recursively split the list into two halves, and we will merge and sort those two halves afterwards. Since we're running with recursion, every time we split the list into a half, that half is going to be split into another half as well, until it reaches this base case, which is when those lists, those halves are split so much that they just become a size of 1. And once it reaches that base case, then it will return back up to merge and sort these pairs or halves of the list. And after every half has been merged and sorted, then at the end it should return back up to a sorted list. The bottom-up approach then, if we look at it as maybe the opposite of the top-down approach, so if we look a little bit closer at the top-down approach, we have this list that we are recursively splitting into subsections and we're merging. The opposite of that, we want to think about, we are starting with splitting into subsections and merging, and then we will gradually get to that sorted list. To give a little bit more detail, a little bit more context, the top-down recursion follows these specific steps. We find that midpoint to create the two halves of the list. So we're creating the first half or first section. We're creating the second section, and we're using recursion. And through recursion, we continue to split up those halves until it reaches some base case. Afterwards, we merge those two halves together. If we think about the bottom-up approach then, through this iterative pattern, we want to think about this splitting of subsections. So we create subsections of a list, and these subsections will actually begin at that base case of length of 1. And after every time we merge and sort those pairs of subsections together, then we go back through the list again, and this time we will increase those subsections by 2. And I don't mean by adding 2, but by the power of 2. So when we split those subsections up, we split them by halves, and we're halving every time. So this time we're increasing every subsection by the power of 2. So the next one, it would be size 2. Next one would be size 4. And then it would be size 16. So it would increase in that manner. And we're also merging those pairs of subsections as we iterate through the list. Again, looking at both the top-down and bottom-up approach, we have to really hammer down this divide and conquer approach to both approaches of top-down and bottom-up. So it's very important to understand the splitting of the list into subsections to really understand how the bottom-up approach works. Then we merge and sort those subsections, and every time we either increase or decrease those subsections, they're always by this power of 2. So it depends on whether it's the top-down or bottom-up approach. So if it's the top-down approach, we're going from the full list, going down by half every time. So the bottom-up approach would start at the 1, going to 2, going to 4, up until those subsections reach the length of the list. Looking at the bottom-up approach, then in this visual diagram, we're looking at this list. And the list is just, these aren't numbers, it's just the indexes of the list. The first loop, just to repeat, the bottom-up approach of merge sort performs merge sort iteratively, so we're going to just continuously loop through this list. And the first loop, we have our subsections be the size of 1. And so we go to every pair, subsection size 1, and we will merge and sort those subsections together. and then we'll go to the next pair, and then the next pair, all the way to the last two elements of the list, and then we'll repeat the loop again on the size of the list. This time, though, we'll increase the subsection to 2, and we'll go through every pair, and we'll merge and sort those pairs, and continue on to this pair, and then this pair, all the way to the last pairs of subsections, and then we continue on the loop until the subsection's size is less than the size of the list. If that's not quite clear, I think when you see a little bit more of the logic and see a little bit more of it in action, it will kind of make a little bit more sense. So the biggest purpose of using the bottom-up approach is thinking about the biggest problem that came with the space complexity using recursion. Using this iterative process has no recursive calls, no memory stacks, so you don't need to allocate any space. Some people might argue that this is also a faster algorithm, but not in terms of time complexity. When you think about not having to use the memory stack, not having to use function calls, not have to use recursion, just computation-wise, it could be technically considered faster, but it's not faster in terms of the big O notation. It would still be the same n log n. And if you had to consider the most optimal solution for a merge sort problem, specifically one with a linked list or something on LeetCode or something that maybe is asking for the most optimal merge sort, this is probably the answer that they're looking for. There are certain limitations and some setup that needs to be done when we think about the linked list bottom-up merge sort. Most times when you look up merge sort online or other materials or references, they usually typically use or assume that you're going to be using an array. And there's a big clear difference between a linked list and an array in that there are some limitations using a linked list, such as there's no indexing. So you can't necessarily assume the start and mid locations of those subsections. There needs to be a specific way to track those subsections within the list and splitting of those subsections without an index. Also, since there is no way to know the beginning or the end of that list, because there is no index, there needs to be a way to track the start of the list, and you can repeat that loop. And you also have to keep track of the start and end of certain subsections within this bottom-up merge sort approach. And so I'm also assuming that there's no start and end on this linked list. You can only access nodes one at a time. There are no functions, methods, or variables that are typically available maybe in an array. We can't assume the length. We can't simply just use a for loop without changing or altering that loop. There needs to be some setup for linked list merge sort if we're going to approach this at a bottom-up approach, if we are thinking about it in terms of the array bottom-up merge sort. We need to keep track of the length. We need to find a way to continue every iteration from the beginning, so we need to find a way to loop through the linked list repeatedly. We need to find a way to track those subsections, the beginning and end, and modify to every length as those subsections grow after every loop and iteration. And we also need to find a way to merge and sort those subsections as we loop through the list as well. The functions that we will specifically focus on through this video and will create will be the get length. So that one just gives you the length of the list. I'm not going to go too much into detail on that one, but I will provide more of the code at the end so you can kind of look at it if you're not 100% sure on how to create that function. This video will focus primarily on these two functions, the subgroup and the merge. So the subgroup should split a subsection on the list depending on a size, and that size is going to be changed throughout every iteration of the list. And so that's how we kind of can split up to those two pairs that we're going to merge together. We're also going to have a merge function that needs 3 arguments. It's going to have the left half and the right half. Those are the 2 subsections that we're trying to merge together. But since this is a linked list, we're also going to add in some sort of pointer, since we need to merge and sort those 2 subsections and halves together. But since we don't have any kind of index, we need to have a way that we can add it to the list without affecting its location. So we need to have that linked list pointer. If that's not very clear, I think once we kind of go through some examples and explain the logic a bit further, it should make a little bit more sense. The variables that we need to consider, just to repeat going through the setup and going through this process of creating and modifying the bottom-up linked list merge sort, is we need a lot of different pointers since we're working with a linked list. We need a pointer to traverse the list. We can't modify those subsections without having a pointer that is also keeping track of the list in some manner. Since we are continuously modifying subsections and portions of the list, we still need to have one pointer that's continuously keeping track of some place or location in the list, so we can continuously put those subsections and merge subsections back in their same place. Then we need to have a pointer that's always at the head of the list, so we can continue back to the head to repeat our loop as needed. And we need to have a pointer to track those subsections, and that's important because, again, since we're using a linked list, it's modified in a way that when we merge and sort and split those subsections, we're going to need more pointers to keep track of those individual parts of the list as well. This is just a general overview of how those functions come together. And so we're just already assuming that we use the get length to understand the length of the list. But when we look at the subgroup, and the subgroup functions are 1, we're going to split those subgroups from the list at that location by 1, split it by 1, split this section, split this section. Then we're going to merge and sort those 2 specific pairs of subgroups size 1. And once we apply the merge function on those 2 subgroups, then we can go to the next pair of subgroups, and we're going to assume that they will be merged and sorted after we have called the merge function. The bottom-up merge sort approach, then, considering all of the factors and setup and limitation and functions we have discussed before, are primarily going to be focused on those 2 functions, splitting up those subsections and or subgroups and merging those subsections and subgroups together. But first, I wanted to talk a bit about, again, reviewing the variables that we have to consider. First, we also really want to focus on tracking the width of those subsections. We're going to track the size after every single iteration through the list. That's going to increase by a power of 2. So it starts at 1, goes to 2, 4, 8, until those subsections exceed the length of the list. We're going to track the start of the list. That way we can repeat the loop of that condition of the subsections being less than the length of the list. And we also have to keep track of the start of those subsections. Since we are using a linked list, we need to have a pointer that tracks the beginning of each subsection. This is just a drawing example, and this is what we're going to look at when we think of the first setup of our bottom-up approach. To begin, we want to have this dummy node that links to our list. And there's a key reason why we have this dummy node that will be highlighted as we go through this logic, and the visual example should highlight why this is necessary. And this is just a rough highlight of the variables that we have so far in the very beginning of this bottom-up approach. So we haven't done anything yet. We have a length of 8 on our list after we called the get length on the linked list. The subsections begin at the size of 1, so that is the very beginning. And this is what we have created when we have created that dummy node. That's going to be before our list. We know that we have this loop that goes through our list until the width of the subsections is less than the length. So we really need to have this while loop be the first outer loop of this bottom-up approach. This is our list with the dummy node. So we also have this pointer that we're going to assume that's going to be at the very beginning where the dummy node is. So this is the outer loop again. So we're going to have some logic that's inside of this outer loop. So we need to keep track of the subsections, just like in the bottom-up approach. So we will use a start pointer to keep track of the start of each pair of subsections between the merge and sort while we traverse through the list. Once the start pointer has reached null, we know we have reached the end of the list. If we are at the end of the list, then we knew we need to restart the loop and iteration and increase the width of the subsections by 2 times, or the power of 2. This start node, or this start pointer, to give a little bit more information and more details, this is pointing to the start of the pair subsection split and merge. Split and merge. So as this start pointer goes through these pairs of subsections, eventually it will reach the end where it will be null. That will indicate to repeat and go back to the very beginning and increase the width of the subsections. So we want to have this while the start is not null, because null for the linked list would indicate that that's the very end of the list. So we want to consider what would be the logic inside of this loop then of the splitting of the subsections and merge. So now we need to consider how we will split the subsections and merge and sort the list in this loop. We know that we have to do a few things within this specific loop. We're going to split between 2 subsections based on the width of the subsections. We're going to merge those subsections together, and then we want to be able to repeat to the next pair of subsections in the list. The logic for the subgroup split is going to be focused on just talking about how those subgroups are split from the linked list. So in our list, we want to only get a subsection of the list without affecting the rest of the list. Each subsection is determined by the width of the subsection given by the merge sort function. As we talked about before, the width is going to change after every complete loop. So since this is a linked list, we are going to take out those subsections within the list itself. This is going to be a visual of that subgroup split. And X is the pointer where it points to on the linked list. We start with the subgroup size 1. As we call this function, this subsection will get separated from the list completely, thus creating one group, one subgroup size 1. Then we will return the pointer to the next element. Thus, we can completely separate this subsection, and we have this pointer here that's still connected to the rest of the list. We're going to call this subgroup again. So we have the first subgroup that's completely separated from the list. We call subgroup size 1 on this pointer x. We are going to separate this subgroup completely from the list again, return to the next pointer, and so now we have our pairs of subgroups in the list that are completely separated from the rest of the list that we can merge and sort. If we look at that splitting from the subgroup, we can clearly see that now we have two completely separated subsections within the list, and we need to put them exactly in their same location, like in the bottom-up merge sort approach within arrays. So we need to have another pointer which will continue to iterate through the list as well from the beginning to the end to make sure that we can place those subsections exactly in the same location as they were taken out. This is just another visual representation. This time, these colors represent 4 different pointers. The red color will represent the subgroup of the first subgroup. The green pointer will represent subgroup size 2. This one will just indicate the start of the next subsection or next pair of subsections. Start of next. And we need this pointer here so that we can merge and sort those subsections back into our list. So once we call subsection subgroup split 1, we're going to have this subgroup here with the pointer still located here at the start. We're going to have subgroup split here. We're going to have the pointer that's still pointed at the beginning of this subgroup here. Then we're going to use this pointer in our linked list to merge these two separated subgroups and have the pointer here at the very end of this merge sorted subsection subgroup, ready to be merged with the next pair of subsections that will be split from the list. We have 4 different pointers. That might be a little bit overwhelming. It's kind of confusing if you think about all different pointers, so it's easier to dissect the pointers, connecting them to that top-down approach. We had that left, which was the first portion of the subsection, the right, which is the second portion of the subsection. We have the next start, which is the next place of the start for the next pairs of the subsection pair that we're going to split and merge. And we have the current location of the pointer in the linked list. Because we don't have an index, we use that current pointer to merge those two subsections and sort them together. And this is kind of similar to the recursive logic of merge sort, thinking about we have a left half, a right half, and we are just merging those two halves together. The logic, now I'm going to talk about the merge function. This is going to talk more about that logic of the merge function. Before, we were focusing only on the subgroup split function. So now we have 2 disconnected subsections within our linked list. and we want them to merge together. If we think about the logic for this merge and the top-down approach, they're going to be the same. The only caveat is that we still need to have the current linked list pointer to safely place in our pairs of subsections without any issues. Because they are completely separated from the list, we need to have that current linked list pointer that's pointing to the current location within the list to be able to place them back in without any issues. The merge logic breakdown then is separated into these sequences of actions. So we want to sort out our two subsections together. However, we will use the current linked list pointer to place them in the original list. After we have sorted and placed the items within the list, we want to iterate to the end of that subsection that we have merged and sorted. This way we can prepare and add to the next subsections within the list using that current linked list pointer. This is just going to be a visual of the merge function in action. So we talked about the red color being the first subsection, the green color being the second subsection. These are just the pointers, also pointing to their location as well. This is the current location of the linked list pointer. So those are our three different arguments. After we have called that merge function from these two already split subgroups or subsections, this is going to iterate through and add and sort to the list. So after it is completely finished, the current linked list pointer now is going to be at the tail of this merged and sorted subsection. So both of these have combined together. And now it should be ready for the next pairs of subsections that will be split to merge and sort to the list again. This is just going to be an example that's going to go through and run through the subgroup split, merge, and also slowly go through the logic with actual numbers and values. This is a linked list. This is just going to be the numbers in the list, and the length is going to be 8. The first thing we're going to do is we're going to have that dummy node created. That's going to point to the head of the list. So the head was 6, if we see here. We're going to have the dummy node. This is going to be the variable called dummy. And we're going to point it to this location. And so we're going to create, we know the width in the very beginning is 1, the length is going to be 8. We're going to initialize our loop. While the width is less than the length, the current pointer will be equal to the dummy. So the current linked list pointer is going to be pointed here. Then we're going to have our start pointer go here. Again, this current pointer is before the head so that it can add those elements into the list, including the head, without any issues. But the start is at this location so that this is where we want to begin splitting those subsections in the linked list. Now we're just going to look at the inner loop here. We have the while the start is not null, meaning that it hasn't reached the end of the list of the splitting of subsections. The left, which is also the subgroup 1, is going to be at the start. So it's going to be here. We are going to call subgroup left width. So the width is 1. So now we're going to split this subgroup, and now it's disconnected from the list here. And now we have the pointer here for right. Then we call start subgroup right with, and we're able to split this subsection as well. And so now the start will be located here to the rest of the list. So to just break it down a little bit slowly, the left will always be at the start location because that's exactly where we had the subsection pair begin. So that's where the first subsection should start the splitting and merging. We call this function. Now we're able to split the first subsection from the list. We call the second subgroup function. We're able to split the second subsection from the list. And from the subgroup, that always returns to the next pointer. So since we called it on left, it will return right here. Since we called subgroup right with, the start will be on the next pointer. And again, the subgroup function depends on the size of the width. For this example, the subgroup size width is 1. If it was size 2, then this would be 2 nodes, but the pointer would still be pointing to the beginning of the list. It would just separate 2 nodes from the list. Now that we've split those subsections here, we're going to merge the left and the right using the current pointer. So from the very beginning, our current is pointed to that dummy node, but we have those 2 subsections that are split from the list. So since they're split from the list, our current linked list pointer can go through and iterate through and sort these 2 subsections or pairs of subsections. In the very beginning, they're size 1, but these could be size 2, 3. They're going to increase through every loop and iteration. They're going to combine them together, and at the end, we're going to see that the pointer is going to be at the tail of this merged subsection, or merged list specifically, ready to add on to the next pair of subgroups and ready to merge for the next sections. So let's just go through it one more time, going at the location here. So now the current node is, or current pointer is located here. Our start is located here. So we went back to the beginning of this loop. So now we're going to place the left pointer here. Then we're going to have right equals subgroup left with. That means that from the left pointer, now we're going to separate size 1, where the 7 is. We want start subgroup right with. Now the start will go to the next pointer. Size width 1. And so now we have our 2 subsections again, and we're going to use merge to merge these 2 subsections together using the current pointer here. A more detailed illustration here, just to repeat, this was left, subsection left, this one was subsection right. and we had these two separated subsections. After we perform merge, we use this pointer to go through these subsections, and our current linked list pointer location will be at the tail of these sorted, paired, merge subsection, and our start is here ready for the next iteration. Another thing I didn't really clarify and explain was when we had that subsection function that returns the next pointer, it's only going to return the next pointer because this is size with 1. But if this was size of 2, let's say our subsection was 2, our subgroup function should return the location of the node where we split off here. So that's a very important distinction. So if we looked closer at how the subgroup is working, where it splits off, it returns a pointer to that location. So therefore, we can split the subgroup and we can have the location for those pointers for the left, right, and start location within our linked list. When the start is null for that loop, we know that we have finished that inner loop. So that means that we have done all the subgroup emerging within one iteration. So we have to go back to the very beginning. That's why we had those variables. I think it was current equals dummy, start equals dummy next. So that's going to reset and restart the loop to the very beginning of the list. But we also will increase the width of those subsections by 2 times, or that power of 2. And we will redo the merge and sort and splitting of the subsections. So that way we start at 1, go to 2, go to 4, go to 8, go to 16, etc., until those subsections are greater than n. So that's why it's still that log n. So we're increasing by the power of 2, just like on that top-down approach we were decreasing by the power of 2 when we have those functions every time we call that recursive merge sort. This is just going to be a run through of the code using this bottom-up merge sort approach on a linked list. And as you can probably guess and tell, this is definitely a LeetCode problem. And I just want to repeat and say that I didn't come up with this solution on my own or didn't come up with this logic by myself. I had to go through a lot of reading of the discussion board, so I want to give a quick shout out to LeetCode and all the users that use it that have been tremendously helpful and useful. Thank you so much to all of you guys. Okay, so first, when we go through this code, we want to go through and see whether or not this exists. So this is just going to be the base case of this function. We're going to go through and get the length of the list to do the iterations because we're comparing the width against the length. So just very briefly, let's go to this length function. We're just going to start at the head, have this variable node, and just iterate until while node. That's the same thing as saying while node is not equal to null in Python. Go to the end, increase length, and then return that number, that length. Again, going back to the logic we talked about before, we're going to create a dummy node that's going to be the start of the list. So we're going to have the dummy next be equal to the head that's called in this sort list. These are the variables that we want to persist continuously within the loop. So we're going to just instantiate these first. Start is equal to none, current is equal to none, width is equal to 1. It's just more important to understand that these are the variables that will continuously persist in our entire loop. So first,
we will continue to increase the bottom-up merge sort until it surpasses the length of a list. So that we talked about the width is less than the length. Width is referring to the width of those subsections. We also want to have current is equal to dummy, start is equal to dummy next. So this is how we can go restart back to the very beginning of the list, so we can continuously loop through those iterations from the beginning to the end. So while start, this is the same thing as saying while start is not equal to null. So we're starting from the beginning of each subsection. It's more clear to say subsection pair. So we're going to create the first group from the start variable here. So left is equal to start. Next, we're going to split that right group from the left. So we're creating the first subgroup here. We're creating the second subgroup here. But these subgroup functions are going to return a pointer to the next place where we can be prepared for that subgroup merge call. And let's look at the code just so it can be a little bit more clear. So the subgroup function itself will loop through to find the node that splits the subsection. So we have to think about the width being -1 from this loop, because one subsection, a size 1, is just the node itself. So a width of 2 in the subsection would be just a node and the next node. So you're only looping one time. So just in Python, again, it's because this loop, I think, is inclusive, I think. Yeah. So we want to have the -1 so that we're just continuously going through the loop and going to the next node, because this subgroup is returning the end of the next subgroup, or it's trying to get you to the next start. And it's going to check while it's in this loop. If the head is at the end of the list, it's going to be null. So that's why I said if not head. Break out of this loop. So we can break early because we've already hit the last or the end of the list. Else, we're just going to keep going through the list until we can reach the point of the width. So again, since if it's already not, if the head is null, then it's end of list. So we want to return none because, there's no subsection to be called at that point. Else, we're going to go to the next node that's going to be the next start of those subsections. And we want the head next to be none because we're totally partitioning and separating the subsection from the list. So head.next is going to be the last node in that subsection. So we're returning the next start of the subsection here. And that's how we split into those two subsections using subgroup left, subgroup right. This is a little bit confusing if you haven't fully understood the logic as well. What's really clear and key is looking at the argument here. Subgroup left as argument means we're separating the left portion from the list, but we're getting the pointer back to the next location where we can separate another subsection. We call subgroup right here in this argument. We separate right from the list in that subgroup, and we're returning a pointer to where we can have the next subgroup call to separate and call. So once we do that, we're going to merge these two subgroups here, and we have to use the current pointer here because this is a linked list. So going to the merge function here, we have these two subsections here, and we have the current pointer location. We only merge left and right from current, and we're using the typical merge from tail call. So we're merging them, and we're using the current, which should be the tail, to add on to the list without having any issues, and we're able to add it to the exact same location through using the current pointer. So we loop until either list is null. So while left is not equal to null and right is not equal to null, this is just how it's written in Python. And so we're just comparing if that value is less than the right.val, then just put that next location as left, and we do the same thing with right. And then we just keep going through the current as well. And then we add on to the rest of the list that hasn't been sorted yet, since if it breaks out of here, one of these is already emptied out. So we add the rest of the list to the current pointer. However, at the very end, we want to find the last tail of this merged subsection so we can connect it again to get ready for the next call of the subgroup and merge. That's why we go while this is not null, continue iterating through this subsection, and then we'll return that pointer. That should be the tail. Since we're doing that, then we're continuously able to go through this pattern of splitting the subsections, and we're also able to merge and traverse this current pointer linked list, or the pointer, the current location within our linked list. After this completely has been done, so once this is finished, we're assuming that the start has reached the end of the list. Now we're going to increase the width by 2 times, and then we're able to go back and repeat to the very beginning because we have this function called here. And then once we're done, we're going to just return the dummy.next here. So I hope that was clear and gave a lot more information on the logic. I know reading and pictures can only do so much, so maybe I hope this explanation just broke down a little bit of the information and helped explain a lot of it, because it definitely does help me understand a lot of this logic and code. But if you have any questions or you want to share some insight, maybe this is not the most optimal or easy way to kind of solve this. Maybe there is an easier way that you found out. Definitely share within the comments section. I appreciate you watching. Thank you, and hope you guys have a nice one.